Hello everyone, and welcome back to this discussion on single variable calculus, and today we're going to be continuing our exploration of some special topics associated to integration. Last time we discussed that not all functions have what we call elementary primitives. That is, just because you have a function that looks very nice, like e to the x over x, it doesn't necessarily mean that its antiderivative can be represented in terms of functions that you know. And this motivated the existence of newly defined functions that sort of represented what those antiderivatives were. So a couple examples that we mentioned last time was the sine integral si of x, which was defined as the integral from 0 to x of sine of t over t dt. And defining this allowed us to say, oh, well, what is the integral of the sine x over x dx? Now you can confidently answer this question with, oh, that's just the sine integral of x plus some arbitrary constant c. Another function that we also introduced was Fresnel integrals, sine and cosine, but I'll just mention the Fresnel cosine integral here, and that was defined as the integral from 0 to x of the cosine of t squared dt. And also, with this definition, you can be like, okay, well, what is the derivative of the Fresnel cosine integral function? Well, that's just going to be equal to the cosine of x squared by the fundamental theorem of calculus, right? So defining these special functions actually gave us more access to answering questions that might come up in a lot of applications. What I want to do today is introduce another function that has so many applications that it's definitely a little bit insulting not to introduce it in a first exposure to integral calculus. So this function is going to be referred to as the gamma function. So definition. So the gamma function, and gamma in the Greek alphabet, capital letter represented by that symbol, gamma function. So the gamma function is the area underneath the curve given by fx of t equal to t to the power of x minus 1 e to the minus t, where t ranges from 0 to infinity. And you're like, well, what's so special about this function? Well, if you look at its graph, it actually looks pretty nice. It looks almost like a skewed right bell curve. If you know anything about probability density functions, it looks very similar to the gamma probability density function. I wonder where it gets its name from. And also the log normal probability density function as well. Right, so obviously it looks pretty nice, and you might be thinking, okay, well, if I want to find the area underneath this curve from 0 to infinity, would it have a nice answer? Well, if you know the gamma function, then yes, that answer always has a nice representation. Right, so the gamma function is defined precisely as the area underneath that curve, in particular t to the x minus 1, e to the minus t dt. Right. So this area here. A couple little observational things that you can immediately see. As the number x gets closer to infinity of this particular function, our function f of x gets taller and wider. Right? So for example, this green curve could be x is equal to 5.1, but if I were to choose a different x value such as this one, then that will be equal to, like, say x is equal to 7.8 or something like that, and the area underneath that curve will obviously grow as well, right? So therefore, as x goes to infinity, the area, which is another way of saying gamma of x, will also get larger. And then I could ask, well, how fast does it grow? And then you could answer with some fancy answer if you know some analytical tools. Right, so a couple little theorems that I will leave to you to prove if you're in the analytical realm. The first thing is that for any x greater than 0, gamma of x is finite. Yes, as x gets larger and larger, it does grow, but it is finite. So since any value in the range of gamma on 0 to infinity is finite, you should be able to represent its graph, which is going to look like this. And a couple other special values of it, and these are just special, but there's several other special values. Gamma of 1 and gamma of 2 are both equal to 1. right? And I highly recommend, if you're still getting used to integration, these are both good exercises for you to prove on your own. So 1 is going to be located here, 2 is going to be located there. Yes, I know it doesn't look like it's drawn to scale, but both of them are going to be equal to 1. Right? Obviously, you see that there's a unique minimum in this curve, and I will give you a few decimal approximations to that number a little bit later. But I definitely recommend you try and prove that gamma 1 equals gamma 2 is equal to 1, and maybe plot a couple other points, maybe in Desmos, to sort of see that this curve is indeed true. Now let's derive another very famous property of the gamma function, and this actually can come naturally to those who think that this actually has an answer that you do not know what it is, provided that you don't even know what the gamma function is. So if you see this integral blindly and you don't know what the gamma function is, what type of integration techniques would you possibly use on this? Well, we know that if we differentiate e to the power of minus t, it will always be exponential. But if we differentiate t to the power of x minus 1, provided x minus 1 is a natural number, eventually it will differentiate off to 0. So maybe integration by parts will give us something a little bit more meaningful for this integral. In particular, you would let u be equal to t to the x minus 1, and therefore du will be equal to what? So keep in mind, we're differentiating with respect to t here. So x minus 1 is a constant as far as we're concerned. So that's going to be x minus 1 times t to the power of x minus 2 dt. So that's going downwards. And then that means dv will be equal to e to the minus t dt, forcing v to be equal to minus e to the minus t. Right? So that sets us up for some integration by parts action. So let's see what that turns into. So it's going to be equal to uv. So minus t to the x minus 1 e to the minus t. And we need to evaluate that as t goes to infinity and as t goes to 0, minus the integral of v du. So we get this. So if we look at this first evaluation, as t goes to infinity, this is going to go to 0. And as t goes to 0, this is going to go to 0. So this entire leading term is going to go to 0 as well. So we don't need to worry about it. Also keep in mind, this is a t integral, so that x minus 1 term is just a constant as far as the integral is concerned. So what we have here is that gamma of x will just be equal to x minus 1 times the integral from 0 to infinity of t to the x minus 2 times e to the minus t dt. Notice that this is just the same thing as the gamma function, except instead of x minus 1, it's x minus 2 now, right? Which is just the same thing as x minus 1 minus 1. So it's the domain shifted down by 1. So x has just been replaced with x minus 1. So that means we can write this as gamma of x is equal to x minus 1 times gamma of x. So we get this identity. Or you can represent it in another way. You can say that gamma of x plus 1 will just be equal to x times gamma of x. That would be another equivalent way of writing it. And keep in mind, x has to be a number between 0 and infinity, right, for both of these expressions. Okay, so once we have this, then what can we build? Well, if we take this identity right here and expand on it, well, gamma of x is just x minus 1 times gamma of x, so why can't I just substitute that here? So gamma of x plus 1 will be equal to x times gamma of x, but gamma of x is just going to be equal to x minus 1 times gamma of x minus 1, and this property will continue so on and so on and so on, right? So we can continue as far as we want. In particular, let's assume that n is a natural number, right? So natural number like 0, 1, 2, 3, 4, 5, and so on. Some people will include 0, some people won't, but anyway. So we're going to have n times gamma of m, and then n times m minus 1 times gamma of m minus 1. And then this is going to be n times m minus 1 times m minus 2. And we can continue that all the way down to, for example, gamma of 1. But we already know, and what comes before gamma of 1, that's obviously going to be equal to 1. But we know that gamma of 1 is just going to be equal to 1. So what we have here is this is just n times m minus 1 times m minus 2 all the way down to 1. So that's what gamma of m plus 1 is. But you should recognize that if n is a natural number, that is just equal to n factorial. right? So therefore, gamma of n plus 1 is equal to n factorial, provided that n is a natural number. And technically speaking, you could say that gamma of x plus 1 is equal to x factorial only for x in the set of natural numbers. When x belongs to something not the natural numbers, then x factorial doesn't make any sense. So let's just do a little example. What would gamma of 5 be equal to? Well, from this identity that we've just derived, I guess you're using mathematical induction, that's just going to be equal to 4 factorial, which is the same as 4 times 3 times 2 times 1, which is 4 times 3 is 12 times 2 is 24. Right, so gamma of 5 is equal to 24. Right. Now that we have some comfortability with evaluating gamma, let's actually prove another value of gamma that's extremely, extremely common. Suppose that somebody asks you, what is the value of gamma of 1/2? Well, obviously, since 1/2 is not a natural number, we can't express it in terms of factorials in a meaningful way. So how would you find it? Well, we know the definition of gamma function, so let's work with that and see if we can get anywhere. So this would be the integral from 0 to infinity of t to the power 1/2 minus 1 e to the minus t dt. And obviously t to the 1/2 minus 1 can also be written as the integral from 0 to infinity of t to the minus 1/2 e to the minus t dt. And you're like, okay, well, I don't like powers such as square roots. Maybe I can use a substitution and get rid of that square root, and that wouldn't be a bad thing to do. So let's assume that t is equal to u squared, so we can get rid of that square root, that 1/2 exponent, out of the picture. So obviously, if t is equal to u squared, then what we're going to have is u is going to be equal to the square root of t. Notice that I don't need absolute values here because t is a positive number, and the absolute value of a positive is a positive, so we don't have to worry about that subtle issue. Also, if t is equal to u squared, then dt will be equal to 2u times du, so that's going to take care of our dt term. The next thing that I need to figure out is what is the bounds? So currently t belongs to 0 to infinity, and we know that the square root function goes from 0 to infinity on 0 to infinity, so that means our u bounds are going to remain the same, 0 to infinity. Technically not the same, but they look the same at least when we write it. So what we're going to have is the integral from 0 to infinity, and that's in terms of u now. And then we're going to have u to the power of minus 1 because our square and our square root cancel. And then we're going to have e to the power of minus, and t is just another name for u squared, and dt is now 2u times du. Right? So this is what our integral has turned into. We have a constant of 2 that can factor out, so let's go ahead and do that so we don't lose it. So we have 2, and we also notice that we have u to the minus 1 u, that's removable discontinuity at 0, but that's not really an issue because on the left bound you have our integration, so it doesn't even need to be considered as long as it's not a vertical asymptote in terms of u, which is not. And then we can rewrite this in a simple way as the integral from 0 to infinity of e to the minus u squared du. Now, when you look at this, you're like, oh, this is an improper integral, so I should be able to write it using a limit, and indeed you can. So we're going to write that as 2 times the limit as x goes to infinity of the integral from 0 to x of e to the minus u squared du. And this should look like a special function that we discussed in our last video on elementary primitives. That kind of looks like an error function. The only thing it's really missing is just a constant in front of it, because for the error function, it has a 2 divided by the square root of pi term in front of it. But obviously we can't just put it there blindly. We also have to multiply by its reciprocal on the outside so it stays balanced, right? So this is a special function that we've already defined because it doesn't have an elementary primitive, so there's no sense in writing it. And also notice that those 2's cancel in the front. So we're going to be left with the square root of pi times the limit as x goes to infinity of the error function of x. And then we just need to take the limit as x goes to infinity of the error function, then we're done. So what does the error function look like? So keep in mind the error function has 2 horizontal asymptotes, one at -1 and the other at +1, and the curve of the error function looks like this. So as x goes to infinity, error function goes to 1. As x goes to minus infinity, error function goes to -1. We're going to positive infinity, so this entire integral is going to be equal to 1, just leaving us with the square root of pi. So therefore, the gamma function, evaluated at 1/2, is just equal to the square root of pi. It's a very beautiful number, and pi kind of comes out of nowhere, right? Now, let's combine this with another integral identity for the gamma function that we described earlier. And let's see if you can figure out what the gamma of 5/2 is equal to. So pause this video and see if you can figure this out on your own. So remember, gamma of x plus 1 is equal to x gamma x, right? So gamma of x plus 1 is equal to x times gamma x. Because we know 5/2 and 1/2 are related by a +2 shift in its domain. So we can write this as 3/2 times gamma of 3/2, but I don't know gamma of 3/2, but I can shift it down by 1 and write that as, okay, 1/2 times gamma of 1/2. And you're like, okay, great. I know what 3/2 times 1/2 is. That's just going to be equal to 3/4. And I know what gamma of 1/2 is. That's just going to be the square root of pi. So therefore, we see that the gamma of 5/2 will just be equal to 3 square roots of pi over 4. Isn't that beautiful? Now, I do leave to you as a fun little exercise that if n is a natural number, can you find a nice representation for the gamma of n over 2, or what we call the half integers? That's a fun little exercise that, of course, I said I will leave to you, but it's a good exercise to practice your integration techniques. Another theorem that I'll put off to prove until later is that the gamma function is continuous and also differentiable everywhere on the set of positive reals. So if I ask you, what is the derivative of gamma at x is equal to 2, there's an answer for that. As a continuation of that statement, that means the derivative of gamma of x, this statement makes sense provided that x is in between 0 to infinity. A couple other places on the negative end, but we won't talk about that now. But it's important to also note that the derivative of x minus 1 factorial does not make sense at all, right? This is extremely bad. Some people will use this, they're abusing notation, because keep in mind, gamma of x and x minus 1 factorial, this is only true if what? This is only for x in the set of natural numbers, right? Because outside the natural numbers, x minus 1 factorial does not make sense. It's not defined. Now you can extend factorials into gamma, but there's infinitely many extensions of factorial, not just gamma. For example, you can do linear extrapolation of those points for factorials. It's not differentiable, but at least it's continuous, right? So why is the derivative of x factorial not exist? Well, obviously, x minus 1 is not continuous on x not in the set of naturals. That means there's gaps between the domain values. And since it's not continuous, moreover, it's not differentiable. Right? Now you can extend it with the gamma, but then you're differentiating gamma, not the factorial. So since the derivative of gamma is defined without an issue, then we can ask the question, what is the derivative of the gamma function? Right? So how would you find the derivative of gamma function? Well, the derivative of the gamma function would just be equal to the derivative of this integral defined function, the integral from 0 to infinity of t to the x minus 1 e to the minus t dt. Now, there is some rules about when you can and when you cannot do this, but in short, notice that this is an integral of t. This is a derivative of x, so technically x and t don't care about each other. So as long as this integral exists to some degree, because keep in mind this integral does exist for x greater than 0, but there has to be some convergent speed things that are also required so that you can take this derivative and pass it underneath this integral sign. But notice that there's both t and x, so do we have to do partial differentiation here? Actually not. So what this expression is going to turn into is going to be the integral from 0 to infinity and then d over dx of t to the x minus 1 e to the minus t dt. Now notice that I've changed my notation for my d over dx here and my d over dx here. This is actually a different type of derivative known as a partial derivative, and what it does in some hand-wavy sense is it ignores t as if it is just a constant. Some people will also call it a partial derivative, which we'll spend a lot of time on later. right? So we can say, okay, well, what is the derivative of t to the x minus 1? So t is just a number, like 2 to the power of x minus 1. Well, that's just the derivative of an exponential function, which we already know is just going to be equal to what? So that's going to be t to the x minus 1 times the natural log of the base times e to the minus t dt, right? So that is the derivative of the gamma function. And you're like, okay, that's cool. So what does this function look like, gamma prime of x? Well, you can, plug in some points. Obviously, it's not going to be defined on negative reals or at 0 since we didn't define gamma on that interval, but it's actually going to look like this, right? That shouldn't surprise you because keep in mind the gamma function had this particular type of pattern where it was decreasing on the left of some number and increasing on the right of some number. And this gamma function had a unique minimum, remember? And this number is approximately 1.4616 approximately, right? Now, from this definition of gamma function, exercise, I wouldn't say it's extremely easy, but to prove gamma prime has a unique 0 on 0 to infinity. And this obviously would prove that gamma has a unique minimum on 0 to infinity, provided that gamma prime is positive on or around. Actually, we can say that it's on 0 to infinity because it's definitely a convex function, right? So that's the gamma derivative, or the derivative of the gamma function. There's a couple other variations of the derivative of gamma known as the digamma function, which is the logarithmic derivative, but we don't want to go into that now. We'll leave that to a later time, but there's definitely a lot more things that can be said about the gamma. But there's one other function that is very closely related to gamma, which is known as the beta function, and there's just a couple things that I want to say about that. So here we have the beta function. Now, a couple first things that I want to mention that are different from the beta and the gamma function. The gamma function goes from 0 to infinity. The beta function goes from 0 to 1. So that's the very first difference. The beta function and the gamma function both have this t to the x minus 1 term, but instead of e to the minus t, it has another polynomial looking term, 1 minus t to the y minus 1. So here, this is a dual input function, or a die input function, or a bi input function. So I have to give you a number x and a number y for you to give me an output of the beta function, right? And that's going to give us the area underneath this curve. And the shape of this curve can vary depending on the values of x and y. But it's very clear to see that this function is going to be defined on the interval 0 to 1. Sometimes it looks like a U, sometimes it looks like a bell-shaped curve, sometimes it can be flat. It can take a lot of shapes depending on the value of x and y, and there's plenty of probability and estimation error techniques that are based on the beta function, which we'll get into in another series. Right? But for any x and y, provided that x and y are both positive, right? So as long as x and y both belong to 0 and infinity, then this function, beta xy, will be defined. So the first thing that I want to do is to represent this beta function as in another way. In particular, I'm going to use a substitution. I'm going to use t is equal to 1 over 1 plus s. So take the video and pause it and solve this equation for s and simplify if you want to. But what you're going to get is 1 over t minus 1. And you might be thinking, why do I want to use this substitution at all? You'll see in just a moment. So that's going to give us a value of s. And also, if I define t to be this way, then dt will be equal to what? So that's going to be minus 1 ds over 1 plus s, the quantity squared. And also, if t belongs to 0 to 1, you should be able to verify that s belongs to the interval 0 to infinity in that order. So once you do the substitution, then you're going to get what? So keep in mind, beta of xy is equal to the integral from 0 to 1 of t to the x minus 1 times 1 minus t to the y minus 1 dt. Now we're going to substitute our value of t, change our bounds, use our dt, and see if it comes out to anything nice. So our new boundaries are going to turn into infinity to 0 in that order. T is 1 over 1 plus s, and that's to the power of x minus 1. And then for 1 minus t, that's going to be equal to 1 minus rt to the y minus 1. And then we're going to have our minus 1 differential of s all over 1 plus s to quantity squared. Now what I want to do is I want to combine this term. And how am I going to do that? Well, I'm going to get a common denominator for that. So I'm going to have 1 plus s minus 1 all over 1 plus s. And obviously you should be able to see that these 1's will cancel, leaving us with s over 1 plus s. So I can write this instead as what? Also notice that I have this minus 1 just chilling here. I can flip my boundaries for my integral with that particular minus sign, and then I'm going to be left with a friendly little integral from 0 to infinity, and then we're going to have 1 over 1 plus s to the x minus 1 once I distribute my power to the bottom only. And then I'm going to have s to the y minus 1 all over 1 plus s to the y minus 1 once I distribute that exponent to the top and bottom of that expression. And then we're still left with our ds over 1 plus s to the power of 2. Notice that 1 plus s is a common base, so I can add those exponents. So the 2 is going to cancel with the minus 1 and minus 1 because that's going to be a minus 2 plus 2, which is going to be equal to 0, just leaving us with x and y on the bottom. So here we have another expression, bxy, or beta xy, is equal to the integral from 0 to infinity of s to the power y minus 1 all over 1 plus s to the power of x plus y ds. Right? So if you see any integrals of this form, then you should be able to be like, oh, that's just a beta function in disguise. Now, with this identity and several other complicated identities that require double integration, and you can, of course, avoid double integration with some other clever tricks, you get a very beautiful connection between the beta function and the gamma function. Because notice, I've transformed my boundaries from 0 to infinity, and I still have this something to the power of y minus 1. So this is kind of baiting a gamma of y term in that numerator. And you can also get an expression for s to the power of x minus 1 on the top as well, in terms of the bottom also being equal to x plus y. So when you combine all of those identities together, which we'll do at another time, you'll actually get the beta xy is equal to gamma of x times gamma of y divided by gamma x plus y. And you can obviously see where this is going to be building from, because we have a gamma of y term in this definition. We can easily build a gamma x term on the top if we want to. And we notice we have that little x plus y term on the bottom, which is kind of chilling in the parameter of the beta identity given here. Right? So this is a very beautiful connection between beta and gamma. But of course, it allows us to evaluate the beta function at some given values, x and y, because we already know several different values of the gamma function at this point. So let's just do a couple closing integrals to sort of conclude this discussion. Suppose somebody asks you, what is the integral from 0 to infinity of x to the power of 4.3 times e to the minus x dx? You should be like, oh, that's just the gamma function, because that's just 5.3 minus 1 times e to the minus x dx, which is just a fancy way of saying gamma of 5.3. And then you can use numerical integration techniques and be like, okay, that's approximately equal to 38.08, but technically speaking, gamma of 5.3 is just fine. And another little example, let's assume somebody asks you what is the integral from 0 to 1 of x to the power of 7 of 1 minus x to the power of 3 dx. And you should be like, oh, that's just a beta function in disguise, because that's technically x to the 8 minus 1 times 1 minus x to the 4 minus 1 dx. And that's going to be equal to what from that identity? Well, technically speaking, that's gamma of 8, or beta 8, 4. And you should be able to also prove that this is the same as beta 4, 8, that it is commutative in terms of its inputs. Regardless, once you use that identity provided, that's going to be equal to gamma 8 times gamma 4 all over gamma of 8 plus 4, which again is the same as gamma 4 times gamma 8 over gamma 4 plus 8. And we already know that gamma 8 is 7 factorial, gamma 4 is 3 factorial, and gamma 8 plus 4 is the same as 11 factorial. right? And we should know how to simplify that, because keep in mind, 11 factorial is 11 times 10 times 9 times 8 times 7 factorial. So we're just going to be left with our 3 factorial on top and a reduced version of 11 factorial on the bottom. So we're going to be left with 3 times 2 on the top, and then 11 times 10 times 9 times 8 on the bottom. And what are we going to have here? So 2 can cancel with the 10, leaving us with 5, and 3 can cancel with the 3, leaving us 3 can cancel with the 9, leaving us a 3 on bottom. So that's just going to be left with 1 over 11 times 5 times 3 times 8, which is just 1 over 1320, right? So that's the analytical value of this function that we got from the beta function, and then that gamma beta identity that we presented a little bit ago. Right? So there's just some special functions that are going to be used in several different applications in the future, but I just wanted to present them here because you can still do a lot of calculus arithmetic with them, even though we haven't really discussed the applications of them quite yet. So I hope you enjoyed this video on a brief introduction into the gamma function and beta function, also the derivative of gamma, and we'll discuss the applications at another time. Hope you enjoyed this video, and I'll see you in the next one. Take care.